For over 85% of the Earth's 4.5 billion year history, the planet has maintained a worldwide greenhouse, with hot and humid climates reaching from the equator all the way to the poles. But every so often, the Earth experiences a reversal. World temperatures drop, and glaciers reach out to clasp the Earth in ice. These conditions have been referred to as an ice house Earth, or more commonly, ice ages. But catastrophic changes to the climate don't happen without a reason, so today I wanted to journey back in time to look at some of the causes behind these glaciation events and see what ice ages might be able to teach us about the future of our planet's climate. The Earth has only experienced 5 major ice ages. The first began 2.4 billion years ago, when the only life to be found on the planet was ocean-dwelling, unicellular, and anaerobic. This all changed when evolution delivered cyanobacteria, the first organism capable of converting carbon dioxide and water into useful sugars with the help of the sun, photosynthesis. The important difference here, however, was in the waste product generated, gaseous oxygen. Prior to this, the highly reactive gas had never before been found in the atmosphere. Instead, methane, a powerful heat-absorbing greenhouse gas, was found in abundance. The only problem was, in the presence of oxygen, methane reacts to produce carbon dioxide and water vapor. Carbon dioxide, while still a greenhouse gas, isn't nearly as good as methane at retaining heat in the atmosphere, while water vapor mostly would have precipitated out of the air and into the oceans, minimizing its effects on the climate. What this led to was the atmosphere being gradually drained of its methane and replaced by less substantial greenhouse gases, until for the first time ice formed on the surface of the Earth, beginning what's known as the Huronian Ice Age. The extent to which glaciers encompassed the planet during this time is not entirely known, as each subsequent ice age tends to remove nearly all evidence of those preceding it. But we do know that after most of the world had been buried beneath ice for 300 million years, the veil slowly lifted and the Earth transitioned back to a swampy, lush jungle. From here, it was more than 1 billion years before the Earth glazed over with ice once again, this time thought to have been caused by an increase in volcanic activity. Now, considering volcanoes have been, and still are, one of the largest sources of greenhouse gases on our planet, this statement at first might seem backwards. But the other major side effect of volcanism is the creation of new rock on the Earth's surface. And while it's easy to assume that after their formation, these rocks remain mostly fixed and unchanging, this isn't true. Different aspects of the environment are always interacting with one another, either physically or, more importantly to us, chemically. You see, carbon dioxide in the atmosphere can react with water vapor to form carbonic acid. When this weak acid eventually rains down to the surface, it interacts with newly generated rock, like feldspars, leading to what's known as chemical weathering. What this does is alter the feldspar into what's known as kaolinite, while producing calcium and carbonate ions, which, surprise surprise, react to form calcium carbonate, another rock. What this means is that the formation and weathering of new rocks can actually draw carbon dioxide out of the atmosphere and lock it away into new rock. And shortly after, as a result, Earth entered into the most severe glaciation event in history, the Cryogenian Ice Age. Glaciers extended as far as the equator, while the ocean became a mixture of ice sheets and slush, sealing virtually the entire planet beneath a layer of ice. But eventually, either by chance or more likely as a result of the extreme resource limitations of the time, this period saw the evolution of the first predatory zooplankton, which could feast on the virtually defenseless phytoplankton, providing for the first time a control mechanism for these abundant photosynthesizers. So, after 100 million years of sustained volcanism, with oceanic carbon retention at an all-time low, the balance of power shifted back towards greenhouse conditions and the Earth thawed once more. The next ice age wouldn't come for another 200 million years, with what's known as the Andean-Saharan Ice Age. And I have to be honest here, not much is known about this period of glaciation. It's thought to possibly have been the result of a massive collision somewhere in the asteroid belt known as the Ordovician meteor event. What this did was send a large amount of debris into the path of Earth's orbit, which over hundreds of thousands of years would fall to the Earth, increasing the atmospheric dust levels to several orders of magnitude higher than what they are today. And when dust is in the atmosphere, the small particles can sort of act like tiny mirrors, reflecting away sunlight before it can reach the surface, basically the opposite of a greenhouse gas. Whether or not this was the main cause behind the third ice age event, we know that only 30 million years were spent under the ice, making this the shortest ice age by far. Not long after this, however, by around 360 million years ago, a new evolutionary path was being explored, which led to another precipitous drop in carbon dioxide and abrupt rise in atmospheric oxygen. For the first time in Earth's history, plants began to grow on land. Before this point, life had essentially been restricted to the oceans, but with the development of things like tree ferns and lycopods, Earth's land masses were rapidly colonized with carbon dioxide depleting and oxygen producing life. Pretty soon, plants were building structures like lignin and cellulose, which, due to their complex structures, have incredibly slow decomposition rates. This means there was enough time for them to get buried, preventing their further breakdown, and storing the carbon in their bodies beneath the surface into what would eventually become coal. As a result, atmospheric oxygen levels rose to over 35%, while carbon dioxide levels fell below 300 parts per million, and the planet entered the late Paleozoic Ice Age. Ironically, it got so cold that many plants had trouble growing, and oxygen content was so high that fires could burn hotter and larger than they can even now, helping to periodically remove vegetation and return carbon to the atmosphere. On top of this, around 25 million years into this icehouse event, the Earth's many landmasses assembled into a single monolithic continent, Pangaea. With an interior too vast for most moisture to seep in from the oceans, the water that kickstarts chemical weathering wasn't coming in contact with the rocks at the core of the land. As a result of having two major carbon sinks weakened, CO2 could once again begin to build back up in the atmosphere. Just a nudge is all it takes, and from here, as some ice melt began to occur, this revealed the darker surfaces beneath, otherwise known as decreasing the albedo of the planet's surface, leading to greater heat absorption, creating a feedback loop until the Earth was again free from ice. From this point, the Earth had to wait another 200 million years before South America broke apart from Antarctica, opening up the Drake Passage and allowing for the formation of the circumpolar Antarctic Current. What this did was isolate the southern continent from the warmer equatorial currents that otherwise would have been forced to circulate around the pole. Cut off from equatorial heat, Antarctica formed massive ice sheets 41 million years before there would be ice found at the North Pole. But slowly, as the continents continued to break apart, the shoulders of North America and Eurasia closed in around the Arctic Ocean, again blocking those warm equatorial currents from entering the waters here. Meanwhile, the Indian subcontinent was colliding with Asia and as a result was building the Himalayas, or in other words, exposing more rock for the same chemical weathering we talked about earlier, leading to more CO2 leaving the atmosphere and therefore decreasing the world temperatures enough for ice to form at the North Pole, officially marking the start of the Quaternary Ice Age some 2.5 million years ago. Due to the recent timing of this glaciation, this is also the ice age we know by far the most about, and some of the ice created during this glaciation is still on Earth today. By drilling into the ancient ice preserved beneath Antarctica and analyzing the composition of the trapped air bubbles, we've been able to determine historic carbon dioxide levels, dust concentrations, and even reconstruct temperature. Now, looking at this, it's pretty easy to see the correlation between carbon dioxide and temperature, but their correlation with dust might not be as obvious. You see, when the Earth gets colder, the air overall cannot hold as much moisture, and the planet as a whole becomes drier, exposing the surface and allowing for greater amounts of dust to be kicked into the air. So knowing this and going back to this graph, what we can see is that there's a spike in dust particulates every time the Earth's temperature reaches its periodic minimum. But what I really wanted to use this graph to explain was the cycle of colder temperatures followed by relatively warmer ones, all during an overall ice age. These cycles are what's known as glacial interglacial, and it's likely that all previous ice ages experienced similar patterns to these. The cause of this glacial interglacial cycle has to do with the way, or ways, the Earth orbits around the Sun. The Earth's orbit periodically changes in three main ways: precession, obliquity, and eccentricity. Now, correlating any one of these cycles to the glacial interglacial patterns is difficult because they all happen simultaneously, and the effects of one may either cancel out or exaggerate the effects of another. But simply put, we can see that the Earth's relation to the Sun is the source of cyclical changes to the Earth's climate. What this also reveals is that changes in relation to the Sun are not responsible for beginning or ending any of the ice ages. If they were, we'd see ice ages not just behaving, but actually occurring cyclically as well. Each one is truly unique. What we can learn from this is that while smaller variations in the Earth's climate can be caused by changes in the Earth's position relative to the Sun, the larger climatic changes, i.e. the ice ages or global warming events, have and always will be determined by the composition of our atmosphere. Using this graph then, we can see that without humans, the Earth would be on track to re-enter a far colder glacial period sometime in the upcoming 50,000 years. But now showing modern carbon dioxide levels, we can see that what we've been putting back into our atmosphere pales in comparison to anything we've seen previously over the past few 100,000 years. And if we've learned anything at this point, it's that because of the Earth's inherent composition, which was determined billions of years ago during its formation, the planet naturally favors greenhouse conditions. Every time the climate has diverged from this, it was in large part due to the removal of greenhouse gases from the atmosphere. And the only way the Earth could return to such conditions was for these gases to be replenished. Today, we're putting this carbon back into the atmosphere and simultaneously reducing the planet's ability to absorb and sequester it. Given enough time, the Earth will react in a huge way to this change for the warmer, which is a problem not because I don't like warm weather, but because humans evolved during and as a result of the icehouse conditions experienced by the Earth historically. These are the ideal conditions for human life, and while the cycles of global warming and cooling have never fully eradicated life on Earth, they have been responsible for mass extinction events nearly every time. Modern humans have been around for roughly 200,000 years, meaning we've witnessed two severe glaciations as a species together, between them fitting the Eemian interglacial, where conditions were more or less similar to what they are today. From this, what we can see is that the climate has been in constant flux for our entire evolutionary history, making it impossible for me to make just a single map to represent it all. So instead, I'll be using this period around 25 to 20,000 years ago as an anchor point, but may diverge a couple thousand years here and there. At this time, around 8% of the planet's surface and 25% of its land was buried beneath ice sheets. For some comparison, only about 3% of the planet's surface and less than 11% of the land is underneath ice today. This difference equates to an additional 56 million cubic kilometers of ice on the planet, which ultimately comes from the ocean. What I'm trying to say is that during this time, the sea levels fell by over 130 meters below current levels, revealing far more land area across the surface of the Earth than we're familiar with today. First and foremost, however, we need to address the glaciers. Obviously, they were all much larger than they are today, but not all ice sheets were created equal. Antarctica froze over 41 million years ago, and for all of that time has maintained ice cover, even while the North Pole remained ice-free. The explanation for this is simple. It's much easier for ice to form on land than it is for it to form over water. What this means is that while the continent of Antarctica itself has stayed icy for far longer than any other place on Earth, the waters surrounding the land essentially act as a barrier for any ice trying to expand beyond this point, and therefore the Antarctic ice sheets didn't actually see all that much growth. Where there were other lands to be found in the south, like the southern tip of the Americas, the Patagonian ice sheet reached far into the Andes Mountains, spanning all the way into modern-day Peru, showing just how vital dry land is for ice to form. Besides this, however, only smaller ice sheets were to be found in the southern hemisphere in places like Tasmania and New Zealand. The northern hemisphere, on the other hand, is where we'll find most of the Earth's land area, which means that's also where we'll find the majority of the new ice. Before even going all the way north, the third largest ice sheet on the planet back then and today can be found over the Himalayas and Tibetan Plateau, forming at this time an island of ice surrounded entirely by cold desert. Besides this, the Laurentide ice sheet extended over most of Canada, with glaciers making it as far as the northeastern United States. Strangely enough, what remained of what's now the US is one of the only places on Earth to have received more rainfall at this time than it does now, causing several of the basins here to fill with excess water. The biggest of which was the Great Salt Lake Basin, which expanded into what's known as Lake Bonneville. Not too far away, the Pyramid Lake Basin filled in as well to become Lake Lahontan. Besides these, numerous smaller lakes increased in volume here as well. But the greatest lake in North America came about as the glaciers began to retreat. Here, meltwaters pooled against the ice, forming Lake Agassiz. The further the ice retreated, the greater this lake became until it had grown big enough to connect with the nearby Lake Ojibwe. As glaciers continued to move, the lake followed until the ice wasn't enough to contain it all, and eventually the lake drained into the ocean some 8,000 years ago. Today, only the deepest remnants of this once ginormous lake remain, such as Lake Winnipeg, Cedar Lake, Lake Winnipegosis, Lake Manitoba, and the Lake of the Woods. Besides North America, another important ice sheet formed over Europe, spreading from the British Isles all the way into Siberia. Depending on sea levels and the state of plate tectonics, the Strait of Gibraltar would periodically open and close, cutting off the Mediterranean from the Atlantic Ocean. Without the influx of water from the ocean, sea levels within dropped, exposing even more land and leading to a breakup of the sea into a series of lakes. The effects of this sea level drop reached as far as the Black Sea, cutting it off entirely from the Mediterranean, leading to a substantial reduction in size here as well. This, however, is where things kind of reverse. Instead of being cut off from the ocean, the bodies of water further inland, like the Caspian and Aral Sea, actually had a new source of water. Each summer, the glacial meltwaters would flood nearly all of the drainage basins here, causing the lakes to expand far beyond their modern banks. When the ice advanced far enough, it could block the Ob and Yenisei rivers, both of which normally discharge into the Arctic Ocean. Cut off from their typical outlets, the water from these and other rivers would also periodically pool, forming in the process the West Siberian lake system. At its greatest extent some 50,000 years ago, this lake reached over 880,000 square kilometers, more than twice the size of the Caspian today. This form of glacial-bounded lake likely would have been common wherever ice overstepped onto land, meaning what I've touched on is likely only a small fraction of the many lakes that could have arisen during times like these. The last major glacier system we'll talk about formed around the Alps, becoming a smaller glacial island entirely surrounded by land. This is worth mentioning because the whole concept of an ice age came about as a result of observations made by scientists visiting the Alps. It was here that they first observed the deposition of large glacial boulders far beyond where modern glaciers sat, and came to the conclusion that there must have been a time in the Earth's past when the glaciers extended much further than they do currently. If we look further east, we can see the Eurasian ice sheet actually tapers off somewhere in the far reaches of Siberia, leaving most of what's now Russia's far east surprisingly free of ice. Now, the initial assumption here would be that temperatures weren't low enough to sustain continual ice growth. But if you know anything about this part of the world, you'll know that it is actually one of the coldest regions on Earth. Switching our map real quick over to average annual temperatures, we can actually see this region is clearly colder than both Northern Europe and North America. What this means is that it doesn't really make sense that glaciers did not form here. That is, until we look at the land itself. With less water in the ocean, the entire Siberian shelf sat above sea level, filling in much of the nearby Arctic Ocean to the north and pushing coastlines further east as well. By further distancing these lands from sources of water, i.e. the ocean, this region became extremely difficult for moisture to reach. This, compounded with the air's reduced ability to hold water, and together means the deep interior of Asia just never received enough snow to begin building up ice season after season. To make matters even less favorable, wind patterns at this latitude blow air towards the northeast, pushing dry continental air out over moist ocean air. Meanwhile, over here, the exact opposite occurs, where moist ocean water was pushed over the land, which explains why we see ice forming off the west coast of North America but not Russia's far east. This is important because the lack of ice combined with lower sea levels led to the formation of a land bridge between North America and Asia, what's now known as Beringia. It was this land bridge that early human explorers crossed to begin populating the Americas, meaning we have this land bridge to thank for an entire chapter of human history. This, of course, wasn't the only land revealed by lowered sea levels. Further down the coast, we can see the shallow seas surrounding Japan were dry at this time too, connecting the islands to the mainland. When sea levels reached their absolute minimum, the lower parts of the Japanese peninsula would connect with Korea to create yet another massive lake in the interior of Asia. The Yellow Sea, on the other hand, was completely drained at this time, connecting the Korean peninsula not only to Japan but to China as well. And sorry Taiwan, but during this time you too were part of mainland Asia. Even further down the coast, we'll find perhaps the greatest reclaimed lands anywhere on Earth at this time, as the shallow waters dividing the islands of West Indonesia dried up, and a contiguous landmass rose to connect Sumatra, Java, and Borneo to Southeast Asia, forming what's known as the Sunda Lands. At its greatest extent, the Sunda Basin could reach as far as the Philippines while never pushing further east than the island of Sulawesi. As a result, it's here that an important natural boundary was formed. Being an extension of Eurasia, animals moved freely between Asia and the Sundaland, populating this region with the animals typical to the continent, such as elephants, apes, tigers, rhinos, Eurasian animals. Past this line, however, only animals originating from Australia and New Guinea had access, which is why you'll find things like marsupials and monotremes over here and basically nowhere else, making what's known as the Wallace Line the natural barrier between two entire continents. The last major island to join Asia was that of Sri Lanka, which tacked itself nicely onto India. And it was only 500 years ago that this changed, when a cyclone came through and washed away the last bridge between the two lands. Continuing west, we'll find the Persian Gulf entirely filled in, turning the Arabian Peninsula into, well, not a peninsula. Around the other side of Arabia, we can see that the shallowest part of the Red Sea cut the rest of it off from the Indian Ocean, turning the Red Sea into the Red Lake, while simultaneously connecting Asia to Africa in two places instead of just one. Africa, on the whole, however, was perhaps the least changed of all the Earth's landmasses, gaining a little ground here and there, but nothing huge, especially when compared to Asia. So moving on to Europe, if it wasn't under a tremendous sheet of ice, you'd be able to see that ocean levels dropped far enough to drain the Celtic, North, and Baltic seas, exposing the lands of Doggerland and connecting Britain, Ireland, and Scandinavia to the rest of Europe, while even creating a few new islands between expanded Europe and Iceland. Even further north, we can see a huge area of land would have been exposed, filling in the Barents and Kara Seas. Though all this new land really did was make it easier for ice to come in and cover it all up. North America has a very similar story actually, where under the ice, virtually all of the Canadian islands became fully connected to North America again, even going as far as Greenland. Besides these expansions hidden under the ice, however, North and Central America weren't changed all that much. We'll find the most notable differences by looking at the Caribbean actually, where we'll see the Florida Peninsula was about 2 to 3 times bigger than it is now, though all of the islands throughout the Caribbean grew in size as well, with Cuba nearly connecting to the extended Yucatan Peninsula and Nicaragua reaching out to nearly grab Jamaica. The biggest visible change to the American landmass, however, and really the only big change to happen to South America, came with the draining of the Argentine Sea, which added over 1.3 million square kilometers of incredibly flat land to the continent, though to be honest, most of this would have been uninhabitable tundra for the most part. The last big change to the continents comes by looking at Australia and New Guinea. Today, we can see only the thin and shallow Torres Strait separates the landmasses, but I'm sure at this point you can guess what's coming. Lowered sea levels closed this gap and connected the two lands into a single continent, while also managing to absorb the island of Tasmania to the south. This continent, given the name Sahul, would have measured nearly 12 million square kilometers, making it roughly equal in size to modern-day Antarctica. Besides those small glaciers found in Tasmania I mentioned earlier, Sahul would have been the largest ice-free landmass on the planet, and therefore the landscape here was largely unaffected by the Ice Age. Beyond the continents, all of the Earth's islands were also changed considerably by the lowered sea levels, but I can't actually go through every single island because there are just too many. So an honorable mention definitely goes to the islands of New Zealand for, at the very least, trying their very hardest to become a continent. While they did manage to unite themselves into a single island, sea levels never dipped low enough for the entire Zealandia shelf to be exposed. So what the planet was left with was a mega New Zealand, measuring roughly 520,000 square kilometers, making it the second largest island on Earth at the time, as many of the larger islands today weren't exactly islands back then. The title of largest island, if you're curious, would have gone to Madagascar, which, while only around 580,000 square kilometers today, would have reached a size of over 700,000 square kilometers back then. Now, beyond all of the glaciers, lakes, islands, and continental shelves, the surface of the Earth was changed in one last considerable way, and that's in terms of its natural environment, or in other words, its biogeography.